Alright, so in this video, we are told that we need to use integration to prove that the circumference of a circle is 2 pi times radius. Well, I mean, if you were taking note in elementary school, like let's say high school, the elementary mathematics, by the way, this is actually the perimeter of a circle. 2 pi times radius is the perimeter of a circle, or it could be known as the circumference of a circle. Now, in this video, we will be using integration to actually prove that the circumference of the circle is indeed 2 pi times radius. Okay, so before we start anything, there are two specific equations that we need to know before getting into the proof. So here's the first one. Okay, so the first formula that we have over here is the arc of any length is equal to the integral from a to b. We're going to choose our bound, don't worry, of the square root of 1 plus dy by dx all squared with respect to x. Okay, so let me just explain this formula quickly. So what is going to happen over here? What is expected of us over here? Well, we know that S represents the arc length, right? Any arc length that we choose on the circle. This is obviously our integral. We should be familiar with this by now. We have the lower limit and the upper limit over here. Okay, so let me keep the mouse out so you can see the cursor. So this is the arc length over here of any part of the circle. We have the integral from a to b. Then we have the integrand, which states the square root of 1 plus dy by dx all squared. Now this dy by dx is actually given by another specific formula that we should all know by now. I bet this looks really familiar, this equation. Well, this is an equation of a circle. This exact circle that we have right here, that's the equation. That's the standard equation of the circle. Okay, so what are we going to be doing? Well, our plan for this video, or for this question to answer, is to make y the subject of the formula such that we can find dy by dx. Right? And we can see that r is going to be a constant in that case, and x is what we have with respect to when we are differentiating. Okay, and that's how we find dy by dx. And then obviously with respect to x is our standard integration. We are going to integrate with respect to x. Okay, so if we see an r, we treat it as a constant. Any other variable or letter that we see is a constant. If it's going to be x, then that is just what we are going to treat as an actual variable in that integral. Okay, so now let me just go into more detail here. We are going to create our limits, okay? So where do we start here? What I want to do is I want to take a segment of the circle, right? This is how we're going to start the proof. So I'm going to take this quadrant here, quadrant 1. This is the arc length of the first quadrant of the circle, right? And what we are going to do is we are going to assume that the circle is perfectly centered at the origin. Okay, so we're saying that this point over here is going to be 0 from where this arc length starts. Okay, and then what we're going to do, we're gonna find the area all the way until this point over here, which we can call r, which is essentially the radius of this circle. Can you see that that distance from 0 to r is going to be the radius? Okay, so that means that our a value will be equal to 0, and our b value will be equal to r, because we're starting from 0 and we're going to r. Okay, so that's just a little bit of an introduction here. And one more thing, before I continue, I just want to point out that what we are going to be doing, we're only going to be working with one part of it, right? This equation is only for one segment of that circle. But what we must do is we need to account for all 4 of them over here. So we're going to multiply this by 4, the arc length by 4, such that because we multiplied this by 4, we will also multiply this integral by 4. And this will help us with our proof when we get further. Okay, so let's get into the proof now. Alright, so where are we going to start? Note how I just put this equation down here with all of the editing that I could, and then this equation here of the circle. Okay, so what do we want to find first? Well, what we have over here, this is going to be equal to, let me just make this a little bit thinner over here. This is going to be equal to, okay, great. So we have 4 multiplied by the integral from r to 0, from 0 to r, sorry, of the square root of, we're going to have 1 plus, now this is where it gets, this is where we have to find dy by dx, right? I can't just write down the equation again, that's going to be weird. So how are we going to find dy by dx? Well, using this equation here, what do we have that's present? We have y and we have x. Isn't that exactly what we have here, dy by dx? We have y and x, right? So what we're going to do, because it's dy by dx, we're going to make y the subject of the formula. But first, we're going to say y squared is equal to r squared minus x squared. And then therefore, what we have over here is we have y is equal to plus minus the square root of r squared minus x squared. Now, this is going to be an interesting part. You're probably going to be asking, which one are we going to choose? Now, I'm going to say it right away. We are choosing positive. Now, the reason why we're going to be choosing positive is because when we chose the arc length of the circle, we chose it in the first quadrant. And as you know, the y is obviously positive in the first quadrant. So we're just going to be ignoring the negative, and we're going to be choosing the positive over here. Okay, so I'm going to show the indication that we chose the positive over here. Okay, great stuff. Okay, we did find y, but did we find dy by dx though? No, we didn't. So we have to use implicit differentiation such that now we get dy by dx is going to be equal to, now over here, we can rewrite this as r squared minus x squared raised to the power of a half, right? Such that we'll get dy by dx. Let me write this a bit neater. We use chain rule. Now when we're using chain rule, we're gonna multiply the coefficient here by a half, which is the exponent, so it's gonna be a half multiplied by the inside of the bracket. We keep the same here, but now we're gonna multiply it by, let me just make a little bit of more space here. We're gonna multiply it by the derivative of the inside. Now the derivative of r squared, because it's a constant, we're gonna make it equal to 0. Okay, so that is equal to 0, and the derivative of negative x squared, this is equal to negative 2x. Okay, great stuff. We can rather just simplify a little bit more over here, so that we get dy by dx being equal to, this is going to be negative 2x divided by, and we're going to have, also, sorry, I forgot about this, by the way, the exponent. This is negative 1 over 2. This means that this negative 1 over 2, it's going to go in the denominator, and it's still a square root, by the way. This is what it's going to look like. It's going to be r squared minus x squared. And this is multiplied by 2 because of this 2 over here, this 1 over 2. I'm forgetting a lot of things here. Okay, so from this point over here, we can cancel out the 2's, such that we are left with negative x divided by root r squared minus x squared is equal to dy by dx. And that is what we have now. Dy by dx is equal to negative x over root r squared minus x. Great stuff. So now from here, we just need to plug it in. Okay? Alright. So now you can see that I've plugged it in over here for dy by dx. Okay. Now from this point over here, we need to continue the integral. This is 4 multiplied by the integral from 0 to r. And then we're going to have the square root of, then we're going to have 1 plus, we're going to square this entire bracket here. So therefore, negative x all squared is equal to x squared divided by the square root of r squared minus x squared. Well, being squared, the square root just falls away. So this is going to be r squared minus x squared. Okay, so let me just make this a little bit smaller here. This is dx with respect to x. Great stuff. And now from here, we just continue going. We need to write this whole expression here in the form of one fraction in the square root, right? So that we can say 4 multiplied by the integral from 0, that is not what I wanted to do, from 0 to r, and then we are going to have the square root of, we can rewrite 1 as what the denominator is by itself, so this is going to give us r squared minus x squared divided by r squared minus x squared, and this is plus x squared over r squared minus x squared. Okay, and this is with respect to x. And guess what? Because since we've done this, the denominators are exactly the same. I'm stuttering. The denominators are exactly the same. So from here, 4 multiplied by the integral from x equals to 0 to r. We are going to have the square root of, now we're going to put the fractions together, such that we get r squared minus x squared plus x squared, because of the plus here, is all divided by r squared minus x squared with respect to x. And what do we notice here? These can cancel out. Negative x, whoa. Before I cancel them out, let me write it properly. This is x squared, by the way. Now we can cancel these because it's negative x squared plus x squared. So we can rewrite it like this. Right, so we got rid of the x squares over there because we canceled them out. Now from here, we can write down, let me just go a little bit up, just in case you're writing. We're going to have equals to 4 multiplied by the integral from 0 to r. And then we're gonna use the property that tells us that the square root of a divided by b is equal to the square root of a over the square root of b. Okay, so that's what we're gonna be applying here. We have a quotient over there, so therefore it's gonna be the square root of r squared divided by, this is not what I wanted to do, divided by the square root of r squared minus x squared. Okay, and this is with respect to x. Now from here, what do we note? This square root of r, this can cancel such that we get r on its own, right? I forgot about the square root. So let's continue, by the way. So this is going to be 4 multiplied by the integral x equals to 0 until r. Over here, I must just remember this is going to be r divided by the square root of r squared minus x squared. Okay, it's a square root. Last time I didn't put the square root in and then I just somehow messed up. Okay, so from here, this is what we're going to be doing. We can do trigonometric substitution. Why? Because we have a constant squared minus x squared. But before we do the trigonometric substitution, this is what we're going to be doing. We see that this r can come out of the integrand because, well, it's a constant. We can take it out. Remember, we're treating r as a constant. So this is equal to 4r multiplied by the integral from x equals to 0 until r. And then we're going to have 1 divided by, and we're going to have the square root of r squared minus x squared. And I think this is the reason why I forgot to put the square in because, well, I mean, I don't know why actually. So here we can do the trig substitution. Let's look at this, right? This is in the form of a squared minus x squared raised to the power of p, right? And p is obviously is just equal to a half because it's the square root. But we're focusing on this right now. Because we have a constant square minus a variable square, we're going to be using sine theta. So what we're going to do is we're going to suppose that x, which is the variable that we're using, is equal to the constant, which is represented as a, which is actually r, in our case over here, multiplied by sine theta. And now what we're going to do is we're going to differentiate. So we're going to have dx is equal to, r is still a constant, multiplied by cosine of x with respect to x. Okay, great stuff. But now we want to kind of like settle things. We don't want to go back to this whole substitution thing again. So what we're going to do quickly is we're going to try and find theta. So we can rewrite this as r sine theta is equal to x, such that we have sine theta being equal to x over r, and then therefore theta is equal to arc sine of x over r. Okay, so now we found theta. That's perfect. That's exactly what we want to do. So that maybe we can substitute back in, right? So now we can do the trig substitution, because now we have x, we have dx, and we have theta. Great. Now we have this is being equal to 4r multiplied by the integral x equals to 0 until r, and then we're going to have 1 divided, no, not 1. We have r multiplied by cosine theta, so we're going to have r multiplied by cosine theta divided by, and then we're going to have the square root of, and we're going to have r squared, which is still the constant, it doesn't change, and then we're going to have x, which is x squared. Well, we know that x is equal to r sine theta, but x squared is going to tell us that it's going to be r squared sine square theta. So it's minus r squared sine square theta. Great stuff. And this is d theta. From here, what we can do is we can say this is equal to 4r multiplied by the integral from 0 to r, And then this is going to be r multiplied by cosine theta divided by, now we are going to take out r squared as a common factor, which you can actually write as r squared multiplied by, because we take it out as a common factor, right? And this is going to be 1 minus sine square theta, d theta. And what we can see over here is that this can cancel these by the square root. It just equals to r. Alright. So from here, because that's equal to r, we can get rid of this square root. And that's just going to be equal to r on its own, like this. And then this is equal to 4r multiplied by the integral x equals to 0 until r. And then what we can see is these can cancel out. Okay. Now we have cosine theta divided by. Now what I want to do is I want you to pay close attention to 1 minus sine square theta. Where do we get this from? Well, if we consider our identity, which goes as follows, it's sine square theta plus cosine square theta equals to 1. We can manipulate it such that we get cosine square theta equals to 1 minus sine square theta. Meaning we have 1 minus sine square theta over here. And that is equal to cosine square theta. So this is how we're going to write it. It's going to be the square root of cosine square theta. This is going to be d theta over here. Now from here, what do we notice? The square can cancel with the root over here. This is going to be equal to 4r multiplied by the integral from 0 to r. And we're going to have cosine theta divided by cosine theta, d theta. And guess what? They can cancel as well. Exactly what we want. This means that we are going to have this being equal to 4r multiplied by the integral from x equals to 0 until r, and this is going to be 1 d theta. And then we can integrate in the bound from 0 to r. So it's going to be 4r multiplied by theta evaluated at x is equal to 0 and x is equal to r. Alright, so from here, we need to evaluate. But we have it with x is equal to and not theta is equal to. Meaning we need to directly substitute back with theta. So what is theta equal to? Whoa, we found out what theta was equal to. It is equal to arc sine of x over r. Arc sine of x over r. So we're going to write it like this. 4r arc sine, so it's multiplied by arc sine of x over r. And this is indeed evaluated from x equals to 0 and x equals to r. Great. Now we can do the evaluation from here. Okay. This over here is going to be 4r. We can take the constant out and then we can write the bracket down. Now we're going to have the first one, which uses the upper limit. We're going to plug in the upper limit first. It's going to be arc sine of r over r. And this is going to be minus. Now we're going to deal with the lower limit, which is going to be arc sine of 0 over r. And close the bracket. From here, we have this being equal to 4r multiplied by. Now we need to consider the following, right? These can cancel out here, this r's, and this will be arc sine of 1. Minus, this will be arc sine of 0, because 0 divided by anything is just equal to 0. Now for this one, we need to consider our sine graph. Okay, so let's look at our sine graph here. Okay, so what we have is the following. We have it starting from the origin, going up like this and like this, right? And then we have it going like this and then like this. It's not the perfect sine graph, but this is what it kind of looks like, right? So I'm going to extend this a little bit. Okay, so from here, it starts from the origin and it goes up, and then it stops here by 1, right? And then over here, it's negative 1. Over here, but the minimum is negative 1 and the maximum is positive 1. Now, if we have arc sine of 1, where is 1? Because it's arc sine, we're going to look from the output, which is positive 1, and we're going to lead to where it is. When y is equal to positive 1, we need to know what the x is going to be equal to. Sorry, if we know what the y is equal to, which is negative 1, the x will be equal to pi over 2. And the negative 1 over here will be where it is negative pi over 2. Okay, So what we are saying is that arc sine of 1 is equal to pi over 2. So this is going to be 4r multiplied by arc sine of 1, which is equal to pi over 2. Minus, and we're going to have arc sine of 0. Well, we know 0 is right here by the origin, and arc sine of 0 is equal to 0. Okay. And therefore, what we're going to be left with is 4r multiplied by pi over 2. The 0 we don't have to focus on. And then these can cancel such that we get 2, and then like that. So therefore, we'll have 2 multiplied by r times pi. But obviously, let's fix that over here. We can say this is 2 times pi times radius. And there we go. We have just proven that the circumference of a circle is equal to 2 pi times radius.